Hey students, in this video we're going to talk about planes and surfaces. All right, so before we get started, what I want you to do is whatever you're writing with, or if you don't have one, grab a pen or something, and all right, you have to be at a table of some sort. So put your pen on the table, and so then look at any point that you want to that's not right by the eraser, the part of your writing utensil that's in contact with the table, and put a point anywhere you want. If you were to take a vector from that point to your pen, pencil, or whatever, you'll notice that the angle between those two things is a 90-degree angle. So we know that that means that the vectors are orthogonal. The property of a plane is that if I have a vector, any point I can pick, if I draw a vector from that point to my vector, the vector that we already have, we're going to end up with two orthogonal vectors. So that's what a plane is. It's the set of points where if I take a point and draw a vector from that point to our existing vector, we get a right angle. Now that's going to mean for us that the dot product is 0. And so when we see this equation for this plane, that's this a times x minus x0 and so forth, what we're really saying is that we have this normal vector ABC. So we have this vector ABC is a normal vector, which means, again, it's just orthogonal to some other vector. And so then x, y, z is a fixed point. But how do I get a vector, the component form of a vector? Then I just subtract the two components of, I subtract the components of the vector. So like x minus x0, that's a component, y minus y0 is a component, and z minus z0 is another component. So obviously we're doing this in 3D. And so what we're really saying is that the dot product here is 0. And so what that's going to mean is that in our formula, a times x0 plus b times y0 and c times z0, that has to equal this value of d that we get, and ABC is just the normal vector that we're given. So for our first example, we have to write the equation of the plane that passes through the point 1, negative 3, 2, and we have the normal vector of 2, negative 1, 1. So if we just follow along with our formula, we have, so 2 is our A, negative 1 is our B, and 1 is our C. So we're going to get 2 times x, I'm sorry, oh yeah, it's 2. So 2 times x minus 1 minus 1 times y minus negative 3, and then plus 1 times z minus 2. Right now it's going to equal 0. Later on it's going to equal whatever value that we get. So, and it's going to give us 2x minus 2 minus y. So that's a plus 3. So minus 3 plus z minus 2 equals 0. So that is going to give us 2x minus y plus z equals, that's negative 5 equals 7. So that is the equation of the plane that contains that point. So if we substitute in 1, negative 3, and 2, we should expect to get 7. So let's check that out. So we get 2 times 1 minus negative 3 plus 2, and so that actually equals 7. So this is the equation of our plane. All right. For our second example, so if I give you 3 non-collinear points, they have to make a plane. So like say we have out in space, actually we can just do example 2. So none of this is drawn to scale. So say point A is here, and then point B is here. Now collinear, if they were collinear, point C could be here, and then we can actually get a plane. But that's not what we're doing. We're saying they're not collinear. So that means that they're all not on the same line. So that means that point C could be somewhere over here. So that means that what we really have is two vectors. We have a vector AB, and then we have a vector AC. And so obviously if we look at if this vector continue indefinitely in this direction and this vector AC continues indefinitely in that direction, what we get is an entire plane made by these two vectors. Like in linear algebra, we would call this the span of two lines, that we get an entire plane. So if I give you 3 points and they're not collinear, the way we find the equation of the plane is that we still need a normal vector. And we should know what vector is normal to two given vectors. That vector is the cross product. So all we have to do is make two vectors from our 3 points and then find the cross product. And that's going to give us the normal vector that we need to write the equation. And then we can just use one of the points. So let's say we'll make our 2 points. So we'll have one vector that's AB. So remember, to get AB, we subtract the coordinates of A from the coordinates of B. So AB as a vector is 2 minus 1, which is 1, negative 1 minus 1, which is negative 2, and negative 4 minus 1, which is negative 5. And then AC as a vector is going to equal 0 minus 1, which is negative 1, 2 minus 1, which is 1, and 2 minus 1, which is 1. If we want to say like U is equal to AB and V is equal to AC, and so the cross product U cross V is going to equal, so we have I, J, K, and then if we're doing U cross V, we write the components of U first and then the components of V next, so negative 1, 1, 1. And so we know that we'll get, for I, we're going to get negative 2 times 1 minus negative 5 times 1 I minus, then for J, we're going to get 1 times 1 minus negative 5 times negative 1 J, and then plus for K, we're going to get 1 times 1 minus negative 2 times negative 1 K. And so this is negative 2 plus 5, which is 3. So we get 3I, and then 1 minus 5 is negative 4. So negative 4 is plus 4J. And then 1 minus 2 is negative 1. So minus K. That's our cross product. And so as a component, that's just 3, 4, negative 1. So now we have our normal vector. We know it's orthogonal to AB and AC. And so now we just pick one of the points and do our formula. So say we choose point A, then we'll have 3 times x minus 1 plus 4 times y minus 1 minus 1 times z minus 1 equals 0 right now. So if we distribute, we get 3x minus 3 plus 4y minus 4 minus z plus 1 equals 0. And so that's going to give us 3x plus 4y minus z equals, that's negative 7 plus 1 is 6, negative 6. So on this side, we're going to get a positive 6. And one thing to check is substitute your points to substitute another point that isn't the point that we started with to make sure it works. Like if we've done our algebra correctly, um, we know that point A is on that is in that plane because that's what we wrote it for. But like maybe check point C. So if we check 3 times 0 plus 4 times 2 minus 2, that's going to give us 8 minus 2, which is 6. So that checks out. And quickly, if we wanted to, we could check point B as well. We get 3 times 2 plus 4 times negative 1 minus negative 4. So that's 6 minus 4 plus 4, which is also 6. So this is us checking point B, and this is us checking point C. So it checks out. So again, the process was we found the normal vector by doing the cross product of the two vectors that were made by the 3 points. We did not have to use AB and AC. You could have used BA and BC, but in some way you're using those 3 letters to make your vectors. Next, if we have a plane that is going to intersect either one of our coordinate axes, so we're talking the x-axis, the y-axis, or the z-axis, that's going to happen when the other variables are 0. For instance, if we're on the x-axis, that means that y is 0 and z is 0. So for example 3, we need to find the general form of a vector that is perpendicular to this plane. So we should know that if we go back to our previous example, the normal vector that we got was 3, 4, negative 1 after we did our cross product. Notice that for our formula for the plane, that the coefficients of x, y, and z correspond to the coefficients of our components of our cross product. So that's our normal vector, the coefficients of the variables. So the general form is going to be, it could be any multiple. So we're going to say the coefficients. Let's write a full sentence. The variable coefficients are the components of a, not the a normal vector for the plane. So what that means is 1, 3, negative 4 is orthogonal to that plane, but it could be any multiple, any vector that's parallel to that. So we'll put a K in front, and we'll put the disclaimer: K is any non-zero scalar value. So B, we have to find the points where the plane intersects each coordinate axis. Let's not do that. Let's say where it intersects, I don't know, we'll say the Z axis. And it's the same process for the X and Y. You just change what variables are 0. So let's call this plane P. We'll call this plane capital P. So we'll say P intersects the Z axis when y and x are both 0. So that's going to mean that negative 4z is equal to 8, and so z equals negative 2. So that means that now a plane and a line are going to intersect either at a point, or the line, they either intersect at a point, the plane itself, or so the line, or they don't intersect at all. So in the case of a point, it's going to be 0, 0, negative 2. That's the point of intersection. So imagine what I'm drawing now is a plane, and then through that plane, I'm going to draw a vector. So this point here is where the line intersects a plane. Now, it could be a point. What could also happen is that our line fully rests in a plane. And so the intersection of a line and a plane is either the line itself or it's a point. Or what could also happen is we could have a plane here and the line could be above the plane, parallel to it, so they never exist. Think about that. Parallel to the plane. Think about what that could mean. Um, so find a set of points for which the plane intersects the xy plane. So on the xy plane, that means that z equals 0. So for our equation, it's x plus 3y. So x plus 3y minus 4z equals 8. So if we're going to intersect the xy plane, it means that we're really operating in 2 dimensions. And so the intersection of 2 planes we're going to find out is itself aligned. So if z equals 0, what that means is that x plus 3y equals 8. That's the set of points. Now we know this is a line. If we write it in the slope-intercept form that we're used to, we would get y equals 8 minus x divided by 3, or if you're so inclined, negative 1/3 x plus 8/3. So that's the intersection of the plane with the xy plane. It's the line y equals negative 1/3 x plus 8/3. Next, 2 planes are going to be parallel if their normal vectors are multiples of each other, scalar multiples then. So, and 2 planes are going to be orthogonal if the dot product of their normal vectors is 0, which means that the angle between the 2 planes is 90 degrees. So for A, we're going to see if these planes are parallel, orthogonal, or neither. So for all of these, we're going to say use the first vector, V is the second vector. So use the first plane, use the normal vector of the first plane. So for example, A, U is 1, 1, 4, and V is -1, -3, 1. Now we can clearly see that U and V are not multiples. So what we're saying is that U is clearly not equal to some number multiplied by V, but maybe their dot product is 0. So that would mean that they are orthogonal. So what we know is that they're not parallel. So then U dot V, that's going to equal 1 times -1 plus 1 times -3 plus 4 times 1, which is -1 minus 3 plus 4 is 0. So because we get 0, we know U and V are orthogonal. We're just going to abbreviate orthogonal with ortho. So for B, we know U is 3, 2, -3, and V is -6, -10, 1. And again, clearly they're not parallel because U is not a multiple of V. So we check the dot product. U dot V is 3 times -6 plus 2 times -10 plus -3 times 1, which is -18 plus -20 minus 3 is what, 41, I believe. Check my math. -18 minus 20 is -38 minus, -41. So not orthogonal. So they are neither, which means they intersect, the planes intersect probably at a line. For C, we get, they're not multiples. So you know what, let's actually do an example where they would actually be multiples. So say we had, I don't know, we'll make it -9x minus 6y plus 6z equals 11. So U is going to equal 3, 2, -2, and v would equal -9, -6, 6. So what we clearly see is that u is equal to -1/3 v. If you take the components of v and multiply by -1/3, you get vector u. So these are, in this example that I modified, parallel. So u and v are parallel. All right, so the next to last thing is we have to find the equation of a plane parallel to this plane that passes through the point -1, 3, 1. So imagine we have a plane here. A plane parallel to it is either going to be above or below it. Now, what that's going to mean is that a vector that is orthogonal to our given plane, so like say this is a plane, we'll call this P. So say this is plane P. So a vector that's orthogonal to P is also going to be orthogonal to this plane Q that we don't know. So what that means is that the normal vector that works for that plane also is going to work for the plane that we want to write that's parallel to it. So what we know is that for Q, we'll say n sub Q. So for Q, our normal vector is 2, 5, -3. So then the equation is what we've already done. So we're going to have 2 times x minus -1 plus 3, nope, not plus 3, plus 5, plus 5 times x minus y minus 3. My apologies for yelling. Y minus 3 and -3 times z minus 1 equals 0. So that's going to be 2x plus 2 plus 5y minus 15 minus 3z plus 3 equals 0. That's the same as 2x minus 13 plus 3 is minus 10. So 2x plus 5y minus 3z equals 10. -1, 3, and 1. I feel like my math is off. 2x plus 2. If we put in, so what's that? -13. It's -10 over here. So yeah, 10. If we substitute, let's go back and substitute in a point. I think I made a simple math mistake. Let's find out. So 2. Oh no, I'm crazy. I was doing math wrong in my head. So this works out, but let's check it to be sure. So 2 times -1 plus 5 times 3 minus 3 times 1. That's -2 plus 15 minus 3, which is indeed 10. I don't know what I was thinking. All right, checks out. So the last thing is if two planes intersect, they're going to intersect in a line. In the process for doing this, but like in class, we'll visualize this. It's hard for me to show because I don't have the like software to do so. But when if you take two pieces of paper and you look, if you could like put one through the other, there's a point. There's a point that's common to both of them, and then that point is obviously on a line because the planes intersect on a line. What's happening is that that point is on a vector. It's on the cross product of the plane because the cross product is orthogonal to both planes. So what we need to actually do here is first find a point that's on both, a point that's common to the plane, and then calculate the cross product of the normal vectors, and then write our equation as we would. So the easiest thing to do is just set one of the variables equal to 0 and use that to do a system of equations to solve, and like we'll see what that looks like. So you could do this with any variable. Let's do it for what's easy. Let's let z equal 0. So let z equal 0, and our reason for this is to find x and y. So if z is 0, we end up with a system of equations that's 8x plus 2y equals 6, and 5x minus 3y equals 25. So now immediately we see that this is 4x plus y equals 3, which is further going to tell us that y equals 3 minus 4x. Now we could use that result in this bottom equation to replace y. So we get 5x minus 3 times 3 minus 4x equals 25. All right, so to not bore you with the algebra, we're going to get 17x, and that's minus 9, so we add to both sides. So 17x equals 34, so x equals 2. And since x equals 2, y equals 3 minus 4 times 2, which is negative 5. So what we just found is that negative 5, write it as a point. So what we've just found is negative, not negative. So 2, negative 5, 0 is in both planes. But what's also true is that this point is on the cross product of the vectors that help form our two planes. So our two vectors are u equals 8 to negative 2, which is honestly just for, you know what, we could, so for smaller calculations, we could write this as 4 negative 1, 4 1 negative 1. So let's make that a smaller calculation because we do have to do the cross product. So that's 4, hold on, eraser. So that's equal to 2 times the component 4 1 negative 1. So we can just keep the 4 1 negative 1, and it's the same thing. So and then v is 5 negative 3 and 4. So u cross v is going to equal, so we have our I, J, K, and then it doesn't matter the order, so 4 1 negative 1, 5 negative 3 4. Okay, the order matters, but either vector is going to be orthogonal, so it doesn't really matter the order that we multiply, and we still get an orthogonal vector. So we're going to get 1 times 4 minus negative 1 times negative 3. I should get more room, so let's write that down here. So we get 1 times 4 minus negative 1 times negative 3, I minus, for j, we're going to get minus 4 times 4 minus 4 times 4 minus negative 1 times 5, j, make sure 4 times 4, negative 1 times 5. And then plus for k, 4 times negative 3 minus 1 times 5k equals, oh, not equals 0, because we're not doing a plane. It's just a cross product. So 4 minus 3 is 1. So we get I, and then 16 plus 5 is 21. So minus 21j, and then 4 times negative 3 is negative 12, so minus 17k. Ugly numbers. So then our normal vector, this implies the normal vector of 1, negative 21, negative 17. And so now our equation is just 1 times x minus 2 minus 21 times y plus 5 minus 17 times z minus zeros. And that equals 0. And again, the reason it equals 0 is that the dot product has to equal 0, which is all we're doing. That gives us x minus 2 minus 21y minus 105 minus 17z equals 0, or x minus 21y minus 17z equals 107. And again, that's pretty easy to verify. If we substitute in 2 and negative 5, 2, negative 5, 0, we're going to get that point. So we know it works. All right, so that concludes this video on planes and equations of planes and things like that. Thanks for watching.